Yes, our next speaker is Misha Lyubich. Actually, I'm supposed to welcome all the students also. We have a this is a great talk for you guys to come to. Misha is a great speaker, and then this particular talk has lots of really pretty pictures with the colors. So we have a kind of a diverse audience. Yes. So yeah, Misha is. I mean, I know Misha since I was a graduate student. So it's my great pleasure to introduce Misha. He graduated from Tashkent University in 1984 and works in holomorphic dynamics and chaos theory. Also, Misha has lots of distinguished, actually I should say you're in Stony Brook. He's a director of the IMS since 2007, I think, replacing John Milner. And he has many distinctions, including a ICM Talk 2014 and a Jeffrey William Prize. Yeah, I expect to be a great talk. I've heard this is a story of the Mandelbrot set
of the holomorphic
dynamics. Okay, so let's welcome Misha.
Thank you very much. Yeah, thanks for this kind introduction. So it is demanding somehow. Now I should not disappoint you. I will not. So yeah, and thanks to the organizers for making this a sort of extremely interesting event, and it's my pleasure to take. So what should I do?
You have to speak louder in general. The microphones are
okay, so well, it is my pleasure to take part in this very special event, and also it is always a pleasure to go back to Toronto. I spent here several happy years, and it is always nice to come back. Okay, so well, so today I will try to give you an overview of the field of holomorphic dynamics. So it is the Mandelbrot set here, the symbol, the iconic image of this field. And so somehow there is a tacit connection between the spirit of this field and the spirit of the field's matter, because there is clearly disproportional number of people associated to the field's matter who had been working, who were working in holomorphic dynamics. And actually, when I put this list up, I send the slides out, I realized that there should be one more name here on the top, and it is Alphars. So the first field's metallist, and he certainly in a very deep way is also associated to holomorphic dynamics, as we will see. Okay, so I will try to give you some big scale overview, starting essentially from the very beginning, and then going through different stages of the development, hopefully looking into some perspective in the future. Okay, so that is a classical period. So the field emerged in the early 20th century in the work of Fatou and Julius. So, and the subject is the dynamics of rational endomorphisms of the Riemann sphere. So F is just endomorphism, and we start to iterate it. That is sort of non-invertible dynamics. The degree is assumed to be at least 2, otherwise it is non-interesting if we consider a single map. We would like to understand the orbits of this map, the forward orbits of these maps. And this is because they have a complicated structure. It is already a chaotic dynamical system. And so we learned from Poincaré that sort of the most efficient way, maybe the only way to start penetrating into chaotic dynamics is through the periodic orbits. So through understanding periodic orbits, so the orbits which come back in finite time. And here is a rough classification of periodic orbits. So it is by the multiplier, the basic invariant. Here is the multiplier, it's just the derivative of the p-fold iterate of the map in any local chart. And there is a rough classification of the cycles. The cycle can be attracting if the multiplier is less than 1, super attracting if the multiplier is equal to 1, repelling if it is an absolute value greater than 1, otherwise it is neutral, and theta is the rotation number of this cycle. By the way, So I actually, before going to the specifics, I want to say a couple of general words why this field could attract so many people. So, and the reason could be that it is a very well-defined field, very special, but it is connected in a deep way to many other fields. So to topology, hyperbolic geometry, of course, various areas of dynamics like hyperbolic dynamics and conservative dynamics like KM theory, and of course to probability and ergodic theory, and also in some deep way, as we see, it is related to physics. So everybody, so people with very different backgrounds can find something appealing in holomorphic dynamics for them. So for analysts, for geometers, for physicists, so there is something appealing, and I think that that is the reason why somehow people of very different spirits, different backgrounds, got attracted to this area. And we will see, I have many illustrations of this statement. Okay, so now back to special definitions. Everything can be introduced very quickly here. Everything is elementary. All motions are elementary. So we have this rough classification of periodic orbits. And so we would like to have a better idea what is a kind of semi-law, how these periodic orbits influence the dynamics. And it is related to the classical Fatou-Julia decomposition, the decomposition into the Fatou set, the set of regular dynamics, and the Julia set of chaotic dynamics. And for instance, attracting cycles are in the Fatou set, and they have basin of attraction in the Fatou set, and this basin contains a critical point. There is some secret connection between attracting cycles and critical points of the map. On the other hand, repelling cycles belong to the Julia set, and actually the closure of the set of repelling cycles is the whole Julia set. It could be taken as one of the definitions of the Julia set. It is just the closure of the set of repelling cycles. And parabolic cycles kind of have a mixed nature. They themselves, they belong to the Julia set, but their basins of attractions are in the Fatou set. There are these petals, flowers of petals of orbits. So in the Fatou set that are attracted to this parabolic cycle. And also in these basins, there is a critical point. These basins, there are critical points. So there is some connection between parabolic cycles and critical points. And neutral cycles is a very subtle issue. So neutral cycles, which are not parabolic. So, well, we remember that parabolic means that the rotation number is rational. I'm not sure I said that. So neutral means parabolic is that rotation number is rational, and otherwise it is irrational neutral cycles. And it is a subtle story. The basic question here, classical basic question, where the map can be locally linearized near such a cycle. If it can be linearized, the cycle is called Ziegel. Otherwise, it is called Kramer. If there is a Ziegel cycle, then it is inside of the Fatou set, and the dynamics all around the cycle is a rotational dynamics, conformally conjugate to the rigid rotation. And if it is Kramer, then it is in Julia set. And dynamics is a tricky dynamics, which is a very subtle problem to understand. And Fatou gave such an estimate that the number of non-repelling cycles, total number of non-repelling cycles, is 2 times the number of the critical points. 2d minus 2 is the number of the critical points. And you see somehow you can see this connection to the critical points. And somehow there was from the very beginning, obviously there was suspicion that this 2 is redundant. They should not be here. But this problem remained open for a long time, whether this factor 2 can be removed. Well, here is just one picture of the Julia set, which is Apollonian Julia set. Here we have 4 super attracting fixed points and their basins, and then pre-images of these immediate basins. And you see, then there is this quite complicated split of the Riemann sphere into these domains, and the boundaries, common boundaries of the union of these domains, so accumulate on the Julia set. And this Julia set actually is homeomorphic in some natural way to the classical Apollonian gasket, and we will see so some reasons for that. Okay, and Fatou specified a very important class of maps, very special class of maps, which are called hyperbolic maps. There are two equivalent definitions of hyperbolic maps. The first definition is orbit of the all critical points converge to attracting cycles. And the second definition is that the map is uniformly expanding on the Julia set. So there is a uniform expansion here. And already Fatou realized that kind of this is in a way simplest class of maps. So for instance, on the Fatou set, everything converges to attracting cycles. And here actually realized that the dynamics, so he did not formalize this, that this dynamics of hyperbolic sets is stable. So if we perturb a map a little bit, then the dynamics will change slightly, but essentially will remain the same. He had this picture in his mind, so I don't think that he actually formalized this picture. But with this picture in mind, he put forward a conjecture, which became known as Fatou conjecture, that actually it generically happened, that stability and hyperbolicity, actually he said stability, is a dense phenomenon in the space of rational maps. So, well, this turned out to be a very prominent conjecture, which is still open. But the nature of this conjecture also became, and the nature of hyperbolic maps became really known much later in the 60s, 70s, when very general theory of hyperbolic maps, it was alluded to in the previous talk by Alex, very general theory of hyperbolic maps emerged in the work of Smale, north of Sinai. So, and the structure of these maps was fully understood. So in particular, in this particular case, the area of the Julia set would be zero. Almost all orbits converge to attracting cycles. There is a nice symbolic model which can very specifically describe this chaotic dynamics on the Julia set, and structural stability was also justified in a very precise way. And it was somehow some naive conjectures in the beginning of the story by Smale that generally this kind of dynamics, hyperbolic dynamics, should be so generic. So in under very general circumstances, the hyperbolic maps should be dense. But then Smale himself and his students realized that it is far from being the case. The life is much more difficult. But in dimension one, maybe there is the conjecture may stand the chance. And actually it was Smale also who realized that and kind of amplified in the 70s the meaning and importance of this Fatou conjecture. That is the only situation, dimension one, when it still can survive, this conjecture can survive. Okay, so well, then what happened with with our field is for some reason the development stopped after Fatou and Julia said. Julia, maybe the reason was that they exhausted. The work was very, very deep, particularly the work of Fatou. It is so three comprehensive memoirs, and there were no tools to move forward in some deep way. So maybe that was the reason, but in any case, essentially the field did not move forward until late 70s, early 80s. But mathematics was moving forward, and as we already saw, the dynamical systems moved forward. Well, so the theory of hyperbolic maps emerged, and ergodic theory, as we learned from the previous talk, also emerged, and all these kind of enlightened one-dimensional dynamics as well. And also, even not less importantly, there were developments in analysis, namely theory of quasi-conformal maps that became the basis for the Teichmüller theory of deformations of Riemann surfaces, and was applied in a deep way to the theory of Kleinian groups. All this happened. So meanwhile, so in the 30s and 50s, 60s, so it was so it gave in the late 70s a very big push to the holomorphic dynamics. And one of the very key events that happened at that time was Sullivan's no wandering domain theorems. So, did I miss one slide? decomposition. So what is that? So hyperbolic. I don't know. That is not the right. Full dynamics. So so sorry. Yeah, no, it's everything is okay. Sorry. Yeah. So in the early 80s, Sullivan proved no wandering domains theorem. Namely, he showed that on the Fatou components, there are no wandering domains that never comes back under the dynamics. And what was the idea is that the main idea is that this theorem is actually exactly similar to the Alpher's finiteness theorem, which was proven almost 20 years earlier, had been proven almost 20 years earlier, and which says that if we take the domain of discontinuity of the action of the Kleinian groups, then the quotient will be the Riemann surface of finite type. And Sullivan realized this connection between these two areas, and then it was essentially straightforward. So of course not really so, but not so difficult to transfer ideas from finiteness theorem, Alpher's theorem, to the holomorphic, to the dynamics setting, and to justify absence of wandering domains. And the method that was used is a method of quasi-conformal deformations. Essentially, it says that if everything goes wrong, if such a wandering domain exists, then our rational function would admit an infinitely dimensional space of quasi-conformal deformations of this, because the space of rational functions of given degree is finite dimensional, then this is a contradiction. Okay, and so here is the illustration of the connection between Kleinian groups and rational maps that became known as Sullivan's dictionary. Maybe it's better to call it Fatou-Sullivan dictionary, because Fatou anticipated this connection, explicitly formulated that there should be such connection and there should be a unifying theory. But here is an illustration that is a classical Apollonian gasket produced by the Apollonian group. And actually the limit set of this gasket, which is this set in blue, it is naturally equivalently homeomorphic to the Julia set that we saw a few slides before, this Julia set. And there is a natural surgery that allows us to pass from this Julia set to another Julia set. And so it is one of the occasions of the method of surgery, so classical quasi-conformal surgery. Here one would need a more general so-called David surgery, whose idea is like that. So we want to construct certain map with certain properties. So we cook it up just in some bigger category, say in smooth category or quasi-regular category, and then we can try to realize this map as an analytic map, as a rational map. And it turns out that these tools of quasi-conformal maps and more general tools allow to do that. And in particular, it allowed Shishikura, this method allowed Shishikura to get rid of this redundant factor 2 in the Fatou estimates. That he proves that the number of non-repelling cycles is actually bounded by the number of the critical points. And up to now, it's a very elementary statement, but up to now, there is no proof which does not use quasi-conformal surgery. Okay, and then there was a very deep theory, so put forward by Thurston, deep ideas put forward by Thurston, and they also were motivated, came from a different field. So again, from the theory of Kleinian groups, and more a sort of even to bigger extent from the theory of hyperbolic three manifolds. And so Thurston applies this kind of, somehow it's well known that Thurston has this geometrization project, the program, geometrization program for three manifolds, and he somehow put forward a similar program for rational maps in some very specific case for post-critically finite branch covering. He proved a theorem. Post-critically finite, it means that the orbits of the critical points are finite. It is the simplest class of maps beyond hyperbolic maps. And somehow he gives some topology, some combinatorial topological structure model for such a map, and asks the question when this map can be realized as a rational function, can be realized geometrically. And he gives a criterion. It can be realized unless there is some specific combinatorial abstraction for this realization. And moreover, this realization is unique unless the map is very special latte counter example. So geometrization exists and unique realization of combinatorial data by geometric object exists and unique essentially always. In this, at least in this setting of critically finite maps. And his method was iteration in the computer. Iteration, he induced some map in the Teichmüller theorem, Teichmüller space, in the Teichmüller space, and reduced the problem to the existence of fixed point for this pullback map in the Teichmüller space. And the argument went like that. If there is no fixed point, then the orbit should escape to infinity in the modular space. And in the modular space, escaping to infinity is very well understood. It is just pinching of certain geodesics. And so, and this pinch geodesic produce some family of curves invariant with respect to dynamics. And that is our combinatorial abstraction for realization. That's a kind of rough idea, but what I want to emphasize for the future, that it uses a kind of near degenerate regime. We assume that some sequence of Riemann surfaces associated to the situation degenerate and analyze how they can degenerate, analyze invariance properties of these Riemann surfaces, and arrive to a contradiction or arrive to explicit abstraction. Okay, that was a theorem for postcritically finite maps, one of the most remarkable theorem from the 80s, but it is also a program. We see that one can ask what will happen beyond postcritically finite, and it is a very big and still wide open program in holomorphic dynamics. We will see further developments momentarily. Let me mention one more development in the direction of the Fatou conjecture that the stability hyperbolicity is dense. So actually, in the form of stability is dense, it was proven in the early 80s by Manesat, Sullivan, and myself that the set of structurally stable maps is open and dense in the space of rational maps of given degree, and the bifurcation locus, the complement of the stable maps, is actually can be described as the closure of parabolic maps. And it is based on the theory of holomorphic motions, which turned out to be a very useful tool in dynamics and in analysis as well. And then somehow the problem of density of hyperbolicity is reduced to show that structurally stable maps are hyperbolic, and it was reduced by Manesat and Sullivan to completely ergodic statement. It's amazing. It's completely ergodic statement about individual map. The question is whether individual map can have a measurable invariant line field on the Julia set. And the conjecture is it never happens unless there is some special latte counter example. Okay. So the previous development from the 80s. So do I have 20 minutes or how much do I have? 15 minutes only? Okay. That is so what I have described so far. It is a kind of general theory from the 80s of rational maps. Some important, of course, most things happen, but it is a kind of a thing that most important landmarks of this of that theory. But also what happened is that people realize that even if we reduce ourselves to completely elementary situation, quadratic family, the simplest nonlinear family of maps, then it is already an extremely rich theory. Everything here can be introduced just in 1 minute, so in a few seconds, because even the definitions of the Julia set and Fatou sets are extremely elementary. So you consider the basin of infinity. Here it is D of infinity. Then the complement of D of infinity is called the field Julia set, and the boundary of the field Julia set, which is also the boundary of the basin of infinity, is the Julia set. That is how this object is introduced. And there is a classical dichotomy that the Julia set is either connected or counter, and it can be immediately recognized by what critical point is doing. If the critical point belongs to the field Julia set, then it's connected. If the critical point escapes to infinity, then the Julia set is counter. And then it immediately brings us to the next definition. Mandelbrot set is a set of parameters for which the Julia set is connected. So, and we saw the picture of this Julia set already in the very beginning. You'll see it again momentarily. But the first kind of non-trivial theorem, which was proved in the early 80s by Doherty, Hubbard, and Sebany, is that the Mandelbrot set itself is connected. So the set of parameters for which the Julia set is connected itself. So here is just some random example of a some hyperbolic Julia set. That is actually Cantor Julia set, Cantor dust, and here is the Mandelbrot set again, surrounded by various Julia sets for each parameter. So here it is 0, there is this for each parameter. So you see Julia sets for various parameters. You can think of this as just vibration, well, highly non-locally trivial vibration of Julia sets bifurcated in an interesting way, sitting over the parameter space, sitting over the Mandelbrot set. I mean, we have here this rabbits, airplanes, dragons. There's Feigenbaum map, famous Feigenbaum map. What we see very, very clearly here is various hyperbolic components of the Mandelbrot set, where the corresponding quadratic polynomial is hyperbolic. Here it has an attracting fixed point. Here it is this fixed point bifurcates to an attracting cycle of period 2. Here it bifurcates to attracting cycle of period 3. Then there is a cascade of double bifurcation, which leads to the famous Feigenbaum map. Here is a cauliflower in the cusp of the Mandelbrot set. So, well, it is on the boundary of these hyperbolic components. But the components of interior of the Mandelbrot set, all components that can be found in the computer are hyperbolic components. So clearly, this kind of confirms the Fatou conjecture in this case, but it still remains open. The question is whether there is some queer components of the interior of the Mandelbrot set. So where the maps filled with the maps which are structurally stable, so which don't change much under perturbations, but which are not hyperbolic. It is an open problem, and up to today. Okay, and then Doherty and Hubbard put up an extremely remarkable conjecture. So if conjectures were entitled to be rewarded with the Fields Medal, I would give this for the conjecture itself, not for any results in this direction, but the conjecture itself, because it was a remarkable insight. So, and they suggested that the Mandelbrot set is locally connected. So, and it looks like a very special property. For them, main motivation was probably that if it is locally connected, that one can build up a precise topological model for the Mandelbrot set. It's very complicated fractal, and still one can describe precisely how this map is obtained by pinching the disk along certain geodesic lamination. So, but also Doherty and Hubbard observed that actually this conjecture is stronger than the Fatou conjecture for the quadratic family. Density of capability or absence of peer components would follow from the MLC conjecture, from the local connectivity of the Mandelbrot set. And also from these insights from Thurston and Sullivan and other people, it became clear that this kind of conjecture is actually a particular case of the most of Thurston rigidity phenomenon, which I alluded to already before. Actually, in this context of the quadratic maps, MLC conjecture is exactly equivalent to the rigidity statement that the quadratic polynomial, non-hyperbolic quadratic polynomial, is uniquely determined by its combinatorial structure. And its combinatorial structure can be defined in various ways, in particular in terms of this Thurston geodesic lamination. Okay, so it became one of the central conjectures in the holomorphic, maybe the central conjecture in the contemporary holomorphic dynamics. And somehow it turned out to be very closely related to another phenomenon, which is easily observed, which stares at us and from the computers, the existence of little Mandelbrot copies inside of the Mandelbrot set. So some subsets which look exactly like the whole Mandelbrot set, and not only topological, not only the shape, but geometry of them looks exactly the same. So you cannot distinguish essentially these copies from the big Mandelbrot set if you look at them just separately without environment. Here is one of the copies. Well, there is slight distortion maybe in this one. There is less distortion in this one. how to distinguish if you are shown the amplified version of this copy, you will see the original Mandelbrot set. And so the question was where these copies came from, why they look so similar to the big Mandelbrot set. And the answer was provided by another remarkable insight. It is the notion of renormalization in quadratic dynamics. And this insight actually ultimately came from physicists. It is our connection to physics. So from the statistical mechanics, from quantum field theories, this Wilsonian Kadanoff picture. So in quantum field theory, statistical mechanics, and it was these ideas were transferred to dynamics by Feigenbaum, Collet-Risser in the mid-70s, who are also physicists. So in a very deep way. So essentially normalization in dynamics means that we built up a transformation, nonlinear transformation that relates various scales of our phase portrait. So somehow there could be some transformation making this relation. And so then we start to iterate this transformation in the infinite dimensional space. And we anticipate that somehow in the limit, asymptotically, we obtain something which is universal, which depends only on the combinatorics of our normalization, but does not depend on particular map in our class. So that is a general idea of renormalization in dynamics. And in the particular case of quadratic family, this idea was very brilliantly specified by Doherty and Hubbard. Also in the 80s, they introduced this quadratic-like renormalization. So you have some, you may have some disk here, which under some iterate is mapped onto a bigger disk as a quadratic-like map with connected Julia set. And if this happens, the map is called renormalizable with certain period, with certain combinatorics. And it turns out that this renormalizable maps, that is another Doherty and Hubbard series, that these renormalizable maps actually are related to the little copies of the Mandelbrot sets. So the parameter belongs to a little copy of the Mandelbrot set, if and only if the corresponding map is renormalizable. And there are two types of renormalization. So when one type is primitive, when the little copy comes from nowhere by the saddle node bifurcation, another type is satellite, where the little copy is attached to some component of the Mandelbrot set. And it could be, it looks like, in this case, you see this little copy does not have a cusp. In the primitive case, it does have a cusp. It looks like a technical difference, but actually there is a very deep distinction, deep difference between these two types of renormalizations. Okay, so it is just some computer pictures of renormalizable maps in the sense of quadratic-like maps. This is the corresponding little copies, and it is just Dublin normalization. The previous normalization was the period 4 normalization. It is just Dublin Feigenbaum renormalization. Here, the corresponding satellite copy of the Mandelbrot set without cusp. And what it has to do with the MLC conjecture. So the connection became clear due to the Yakos theorem, which was proven in the early 90s. And he showed that the Mandelbrot set is locally connected at any points which are not infinitely normalizable. So the main tool was some puzzle partitions, which in some natural way allow to partition to analyze small-scale structure of the Mandelbrot sets relating various scales. But what is extremely remarkable is that it connected the MLC conjecture to the renormalization theory. So now what is left is renormalization theory. Now, at this point, from now on, the MLC conjecture has became part of the renormalization theory. And here are some developments. It's actually development on the real line, so I don't have much time to say about that, but using the Yakos puzzle, so I gave a kind of some complete description of the dynamics in the real quadratic family from the probabilistic point of view. Every map is either regular, almost all orbits converge to attractant cycles, or stochastic. Almost all orbits are equidistributed with respect to an absolutely continuous invariant measure. And actually later we kind of generalize this to generic unimodal maps jointly with Wellington de Melle and Arthur Avila. And it is a kind of occasion of maybe the first occasion when the Kolmogorov's probabilistic viewpoint on dynamics was justified in this very specific one-dimensional elementary situation. But now let us go back to the MLC problem. So after what happened after Yakoz's result, we start to develop the normalization theory, and very much depends on the combinatorics of this normalization theory, whether the relative periods, whether this normalization, we are dealing with infinite normalizable maps, and the periods of this infinite of these normalizations could be bounded. It is a bounded case, so they can be unbounded, and they can be subtilized, they can be primitive, and how difficult the problem very much depends on these kind of conditions. And one of the theorems that we proved with Jeremy Kahn in the 2000s, about 20 years ago, is that if we stay away from the molecule, if combinatorics of normalization is definitely primitive, so the corresponding little copy of the Mandelbrot set stays away from the molecule of the Mandelbrot set. And molecule is everything which can be obtained by these immediate bifurcations from the main cardioid and taking the closure. So it is where the satellite normalization is focused. We should stay definitely away from that region. Then if all normalizations involved are of this definitely primitive type, then we are in business. Then MLC holds in these parameter values. And it was done in the near degenerate regime. Again, we analyze Riemann surfaces that appear naturally under normalizations, and analyze how these Riemann surfaces can degenerate and how this degeneration is respected by the dynamics. Okay, so here is again a picture of the Mandelbrot set. We see the molecule. Actually, the main thing that we see here is the molecule, but there is a lot going beyond molecule. Molecule stops somewhere here, and there is a lot going on. And if we stay away, we are good. And then the next question, the opposite question: what happens if we are on the main cardioid somehow? And here on the main cardioid, we are dealing with the neutral dynamics. With the neutral dynamics, where we have these parabolic maps, Ziegel maps, Kramer maps. And the local theory for these maps was developed also by Yakoz in the 80s. Namely, he has given arithmetic condition for linearizability. And this theory, it is so-called Bruno condition. And this theory was strongly based on a notion of so-called sectorial renormalization. Also renormalization, but which can be defined which is defined in a very different way from the quadratic-like renormalization that I described before. Here is a picture. You may see so illustration from this picture, but I don't have time to go in the detailed definition. So it is just some pictures of what is happening when we go along the cardioid. Here we have a cauliflower. It is when we go a little bit off cardioid, it is bifurcation of this cauliflower. It is a herd of elephants marching from the cusp of the Mandelbrot set. And it is Ziegel map. Ziegel map is golden rotation number, where for which there is an explicit model given by the quasi-conformal surgery. Dodij's quasi-conformal surgery produces explicit model for this Julia set. And this Julia set has self-similarity features, which are controlled by certain normalization theory, also sectorial normalization theory. So, but not of local nature, but some semi-local nature. And it was it was initiated, this kind of renormalization. It was originally initiated by physicists, but in this context by Kurt Macmillan. So in the 90s. And it is a corresponding parameter picture. That is the main cardioid, and we have self-similarity on the main cardioid. And with Dima Dudko and Nikita Seligen, we developed some also sectorial renormalization of some more global type, which we call Pacman renormalization, which allowed us to control this parameter pictures. And so parallel, independently, before actually, in 2005, another very big breakthrough was done by Ina and Shishikura, who proved a priori bounds for rotation numbers, for quadratic polynomials with rotation numbers of high type. All entries of continued fraction expansion should be high. And the meaning of that is that we are close, that all normalizations are close to the cusp of the Mandelbrot set, close to the multiplier 1, to the parabolic point. It's perturbative theory, but very powerful perturbative theory, which allows to develop more or less full theory of such maps of high type. And very recently, with Dima.co, we kind of extended this kind of sectorial a priori bounds to arbitrarily neutral quadratic polynomials. I should have said neutral quadratic polynomials with arbitrary rotation numbers. Completely different method. The method cannot be perturbative. It was the method again of near degenerate regime, which was applied first time to this situation. Okay, so this result with Dima essentially opens an opportunity to understand what happens on the main cardioid. On the other hand, I'm stopping in 2 minutes. So on the main cardioid, on the other hand, we understand what happens when we are away from the main cardioid, and so it suggests some quite clean path to possible path to the MLC. So somehow from the main cardioid, one can go to the satellite renormalization and to prove some sectorial a priori bounds in the satellite case of the type that we did with Dima on the main cardioid. And then one can interpolate with our old result with Jeremy Kahn and new result with Dima, somehow to analyze non-definitely primitive renormalization as some perturbation of satellite. And we are quite hopeful that there is a chance that the steps can be realized in some feasible future. Okay, so, well, I don't have time to say about one application, one very interesting application of renormalization ideas. It is to construct measures, Julia sets of positive measure, but so the first examples were constructed by Buff and Cherita, and then we come up with examples which are very robust and visible with Artur Avila. So using the renorm random walk idea. So it is just illustration of a black hole associated to a Julia set of positive area. Unfortunately, I don't have a minute to say more about it. And because we are supposed to say about past, about current and future, so here is possible futuristic M theory of everything in one-dimensional holomorphic dynamics. And you see here that MLC is somewhere in the middle. It is certainly the most famous and very prominent problem, but actually it became, as I hope I explained, part of the normalization paradigm. And this renormalization idea is more central than MLC and even to the rigidity idea. So, and hopefully, eventually, everything will become a natural consequence of a general normalization theory, first in dimension 1, but it certainly has an importance beyond dimension 1 as well. Okay. Sorry for